Hello, today I'm going to be talking to you about factor groups. I've taken the time to write out the formal definition from the textbook of a factor group, which to me is very drawn out, lengthy, complex, and frankly confusing. So simply stated, a factor group is a group where G mod H, that's what that means, where G mod H is a normal subgroup of G. So we can delve right into what does it mean to have a group and what does it mean to be normal. But you should also know that factor groups are also recognized or called quotient groups because the group or an integer is able to always be divided by the quotient, which is the subgroup. So that's why those words are sometimes interchangeable, the word factor groups and quotient groups. So we know that groups are defined by four properties. I'll just write that here. Groups are closed under the binary operation, which can be different depending on what the group is, but it will always need to be well defined. So we know that groups are closed, they are associative, they all have an identity element, which leads to us having a inverse for every element. And this is how you have a group. So as I was saying earlier, a group G mod H is a normal subgroup of G. So again, to review, a group is defined by four axioms, closed under a binary operation, the associative property holds, there exists an identity element, which we normally refer to as E, and there exists an identity element for all elements within the group G. So we know that cosets partition a group. They're basically a special form of a subgroup or subset. A subgroup is normal if it is defined by G times H equals H times G. So by definition, every factor group has to be an abelian group if it's following this definition, because like I said in my simply stated definition, a group G mod H where H is a normal subgroup of G. So we know that every factor group or quotient group is going to be abelian and follow this definition of normal. And we know that elements in a factor group are cosets of G and they look like GH. So earlier in this semester, we learned about AHA, which is basically where you have a left and right coset. Well, basically that same rule applies here in factor groups, and it's probably the easiest way for a student who's been taking this course to kind of get a firm grasp of what's going on. Because what we'll see in a few seconds when I get into the actual problem we'll be solving, you see that you take your coset and you're multiplying it times a number which is in the bigger group. But we're going to dive right into the exam. Alright, so now we're going to be diving right into the problem from the book where we are tasked to find the order of Z4 cross Z2 mod the cyclic subgroup generated by 2, 1. So looking at this, we know that this is our group, G, so I'll just write that. And then here we have our subgroup, H. And in this problem, to find our order, the first thing we want to do is write down the formula for that, which is the order of K equals the order of G over the order of H. So, how do we figure that out? First, we'll go ahead and write it out formally. So we have a lot of repetition here. Alright, so to figure this out, we first need to figure out what is the order of the group G. And it's very simple. You just take the two numbers that is the mod of Z. So here we have 4 times 2 equals 8. So the order of the group G is 8. And for 2, for the H, the coset, the subgroup, it's going to be a little bit different in that we will, and then here with H, it's going to be a little bit different in that we actually have to do a little bit of math to figure this out. So we have 2, 1. So we know that that is automatically going to be one of our H's, or that we're going to be manipulating. And then the next thing you want to do is add this to itself to see what happens. So when you add 2 and 2, you get 4. But since this number corresponds with this modulo addition, then you'll see that 2 plus 2 equals 4, 4 minus 4 equals 0. And the same thing happens when we add 1 plus 1, which is 2, which puts us again back at 0. And since this is the identity for a modulo addition, we know that we can stop here. Had these numbers been a little bit bigger and we were able to add to it a few more times, then wherever we ended up back at our identity is what we would have called, the order. But since we literally only go twice here, we know that this is the order of H, and that we can count. This is 1, 2, so the order of this is 2. And based on this definition, this is our K, which equals 8 over 2. Thus, the order of this group is 4, but we're not going to stop there. I'm going to go ahead and write out the elements for you. So to do that, we take our H, which is 2, 1. Let me see if I can clean this up a little bit so it's easier to watch what I'm doing here. Okay, so we take our H. Like I said, this is kind of like the aha thing that we've seen throughout the semester. So we're going to take our H and first add 0 to that. So we'll have actually, we're going to be adding 1, and I said 0, 0. So these are our two, the order of our group, which is made up of these two cosets that we're going to be using, or making cosets out of. So we're going to have 0, 0, and 2, 1, and we're going to first add 1 to it, and then we will take these same two expressions and add 2 to both of them. So doing that, we have 0 plus 1, 0 plus 1, and then we have 2 plus 1, 1 plus 1, and again, we're going to do 0 plus 2, and then 0 plus 2 again, and finally 2 plus 2, and 1 plus 2. All right, and then after doing some quick addition, we will end up with 1, 1, 3, 0. Again, this is going to be modular addition. Modulo addition is the binary operation for factor groups, so that's what we're going to be seeing throughout this whole problem-solving process. And so here when we added 1 plus 1, that gives us 2. However, that's 2 mod 2, which is 0. So there's that. Then we'll have 2, 0 for the same reason. And then finally 0. That comma shouldn't be here. 0, 1. So these are the elements of our factor group for this problem, Z4 across Z2 mod the cyclic group generated by 2.
Alright, so while you blinked, I went ahead and put problem
from number 4 on the board because we were instructed to compare to number 4. The big difference you'll see in 4 is that you were given a set cross Z5, and so in looking at the order of that group, obviously the order here can only be 1 because there's only one element. Cross here we have 5, and so the order of number 4 is going to be 5. So that's the biggest difference between number 3 and number 4. So going backwards, we have explained the definition and components of factor or quotient groups. We have explained how to identify the elements. Here we wrote out all the elements for this problem, and we compared number 3 to number 4 out of the book, and we've determined the binary operation for a factor group is modulo addition. And the next thing that we're going to do here is add elements. So when you do this, we'll just do these two at the bottom for an example, it's still modulo addition. So what you have here, this is easy, we're not going to have to do anything fancy, is this just goes to 1. And what that gives us is H in this case. And then another thing that we wanted to do here was find the order of an actual element. So for that, I would choose here. So a definition for that, I'm going to go ahead and erase so we can have a little bit more space when we do an explanation. Okay, so to find the order of an actual element, what you have is HA raised to n, where n is the order of the element. And what you're doing is you want to have this equal to the identity element. So what that says is H, which is being manipulated by an A. So here our ha was +1 with this portion of our H, 0, 0. So when we added 1 and 1 to our H, we got 1, 1. And the M in this case is what's going to be our order for this particular element. And what the order is going to do is get us back to the identity element. So for addition, we know the identity element is 0. And so how many times is it that we're going to have to add this particular element to itself to get back to 0? So we have 1 plus 1. We have 1, 1. And then if you add that, here we'll have 2. And this is 2, but we know that we're in mod 2, so that's going to be 0. And then if we do that step again, because this will be identical to doubling it, so instead what I'll do is just actually double it. So when we add these two, we're going to be in mod 4, so 2 plus 2 equals 4. In mod 4 is 0, and 0 plus 0 equals 0. And so what we've seen happen is, this is 1 time, and 1 time, and then this is another time of adding it. So we have 1, 2, 3, 4. So M in this scenario equals 4. So the order of this element within our subgroup as a coset is 4. So the last two things that we need to do before we can consider ourselves finished with this task is think of an example of a not factor group. So factor groups or quotient groups is all about being able to divide by our cosets, what we've partitioned the set to be. All of these are quotients of this group. So if we think, what does it mean to have a quotient? If you have a prime number, we know that that number isn't going to be divisible by anything except for 1 and the number itself. So behind that logic, it's safe to say that something like this, let's go ahead and make that parentheses. Something like this probably would not be a factor group because these are 2 prime numbers. Here we should probably have cross. So those would probably not be factor groups. And then one other thing that we needed to identify was what is an element that is not within this factor group. So a good example, we know that 3 is in mod 4, and we know that 1 is in mod 2. However, 3, 1 does not show up in our list of elements. So this is not within our factor group. And that's not, again, to say that it's not an element of the group G, but what it does mean is it's not a quotient, or it's not, G is not divisible by this particular element, and so it's not considered an element of our subgroup.
Okay, I'm sure at this point you're probably tired of hearing me talking, so in summary, I've pretty much left everything that we've gone over today. So we're going to end with my simpler definition of a group, which is a group G mod H, where H is a normal subgroup of G, and we have normal defined here as normal if and only if GH equals HG for all G of the group G. Okay, so where H is a normal subgroup of G, and my little addition to that is that this subgroup contains all possible quotients when dividing an integer, the group G is our integer, by a multiple, the subgroup H. And looking here, I kind of put in quotations the way that we read this, because I know that when I first started trying to solve this problem, I didn't even know what it was that I needed to say. So we have Z4 cross Z2 mod, the cyclic subgroup generated by insert numbers or insert anything, because you can have things other than just a little simple expression in parentheses. So this is a formula for finding the order. As far as the group, if you are given two Z mod so-and-so, you would just take these numbers and add it, and then if this is the way that your group looks, you're going to see how many times you add this number or this subgroup to itself to get back to 0, 0, okay? And I know throughout the video I may have struggled with calling it what it is, but this is a cyclic subgroup, and what we have when we're solving these problems is the elements, the cosets that we break up as we partition the group G into our factor groups. So I think that's going to be all for today and forever. Thank you for watching. Bye-bye.